Thank you for joining us today. It's the fourth lecture, and let me start with a brief review of the last session. This is the session for today, and please tell me if you have questions of the last talk. In the last talk, we discussed mainly the characteristic of the power spectrum in terms of the spectral characterization. In the spectral characterization, we review that the people before 1981 works in terms only the Fourier transformations. They try to write the equations, the generic equations of the generic quantities in terms of Fourier transformation to describe how the density or the pressure or other features of the structure in the universe changes above the full sphere. And they try to relate this quantity with the density and with the temperature. And using the Harrison-Seldovich spectrum, they connect, or they obtain a connection between the observations remember that the part of the observations are codified with the temperatures on the whole CMB sphere, and they try to put indirect with the Newtonian potential. Yesterday, I read at the end a couple of questions about this quantity, and I thought that the question is because we haven't studied the perturbations of the metric. So in this lecture, I'm going to start describing the perturbations part. I know that many of the students here are attending the course of perturbations theory after this course, but let me talk about this quantity in terms of the perturbation theory, and then we come back to this part and try to see again the connection between the temperature, which is a characteristic on the CMB, and the connection with the theory. But again, we study the expansion of the universe, but also we study the spectral characterizations in terms of the density quantity. So it's the 4 presentation, I think it's this. Okay, lesson 4. As we discussed in the previous lecture, the inflation period has mainly 2 advantages. One of them is try to solve the naturalness problem as the horizon problem using this period in which the universe suffered an accelerated expansion. And the second feature, or the second success of this model, is that the model is capable to give an explanation for the primordial cosmic structure. But first of all, we're going to consider the perturbations of the metric. In the first class, we study the Friedmann-Lemaitre-Robertson-Walker metric, and we describe a universe with 2 characteristics: the invariance on their rotations and on their translations. And we codify that symmetries using a maximal symmetric metric. And we studied the three cases, but one of the question was, what is the reason? Because you are considering that kind of symmetries in the space-time. And at that time, I answered the question and I said, okay, because the people thought in a large scale, we can see the whole universe with that kind of symmetries. But in this case, if we are interested in the study of the emergences of the structure, we need to focus in particular regions of the space-time, and the symmetries that appear in the whole space-time are not enough. So we need to perturb this quantity, the metric of the space-time, and also we're going to consider the perturbations in the field. As you can remember, in the case of the field, this is the inflaton field.
Okay.
Go ahead.
What's my name?
Sorry, I didn't hear you. Can you repeat, please?
Maybe that was unintentional.
I thought. Okay. As you can remember, yesterday we studied the expanding period of the universe, and we mentioned the following. The inflaton is the matter field, is an scalar field that characterizes the matter sector in the early universe after the Planck era. And the zero mode of the inflation field is responsible to generate the expansion of the universe. I mean, is the mode that we think is the responsible to dilute all the inhomogeneities and isotropics. So this mode carries from one inhomogeneity and one inhomogeneous and isotropy state to a big patch in which the universe has the characteristics described or codified in the Friedmann-Lemaitre-Robertson-Walker metric. And this first mode is responsible for the expansion. And the other modes are responsible to generate the structure. But when the inflation starts, we thought that the other modes are in the so-called Bunch-Davies vacuum. So in other words, this mode can solve the naturalness problems as the horizon problem, and the others could give you the structure, the good explanation for the structure. So let me start with the perturbations of the background. I thought yesterday, I thought I can use this equation and do the analysis in terms only with this, but maybe could be useful if we study from where this equation came. And I'm going to present the Weinberg's analysis of the perturbations, and we're going to start with the standard background that we study in the first lecture. As you can see, in this equation is right in terms of the physical time, but then I'm going to perform a change of variables in terms of the conformal time. And we can write this metric in terms of a general perturbation. As I mentioned before, many of yours attended the course of perturbation theory, and you can see the relations. I consider a general perturbation. I mean, in all of the terms appears this kind of perturbation term. You can argue that, for example, in this case, we don't have the cross terms, but let me consider this kind of perturbations, even if we have a different term here with evolves across terms. But in the Friedman, Demetrius, Robertson, Walker metric, we don't have that kind of terms. Okay, now to simplify the procedure, let me write each of the perturbations in terms of components. And for example, in this case, we're going to write in that form. You can see that the perturbations depends on time and depend on the space. And in this case, we can think the derivation of this component equal to 0. And you can write from this expression and try to connect with the general perturbation. The people have known very well this treatment, even for the case of the spectral characterization, and they try to write the whole metric in terms of perturbations. But the question here is, okay, we could have the full or the general form for the perturbation metric, or for the perturbed metric, but what are the perturbations in which we're going to interested here? Because you can read all the perturbations from this expression, and also you can read in this form all those kinds of perturbations. But you can see that we can take the conditions on this expression. For example, I'm sorry. No, it's not a question. We can read the derivative of this side, of this term, and also the derivative to this part that will be the tensorial part, equal to 0. And we can consider that the sum of these terms also is equal to 0. And we can classify the components in terms of vectorial, scalar, and tensorial perturbations from this expression. So for now, this expression codifies the changes in all kinds of disturbances of the metric. For example, you can think in two scenarios. One scenario is one sphere. If we thought that I'm in this case, I consider the case in which K is equal to 0 and represents the flat universe. But in order to get a picture to analyze this kind of perturbations, we can think in one perfect sphere, and then, for example, imagine a real Earth or real planet with mountains and with changes from the perfect sphere to the real scenario. So one way to characterize the difference between the real and the perfect model is using a perturbation, all kinds of perturbations, the scalar perturbations, the vectorial perturbations, and the tensorial perturbations, to get a notion of what is the difference between our perfect model and the real description of the situation. So in order to have that difference, we can write the metric in these generic forms. In these forms, you can see that you have cross terms. Again, in this case, we don't have that kind of terms, but it's or could be would read the full metrics, and also if you were attended the other course, you can compare the differences between the perturbations here and the perturbations in the other scenario. But let me show you. In this case, I'm going to say that this A, F, A, and B that appears from this part and in this other part are known as scalar perturbations, or the scalar coefficients for the perturbations, while these G and C are known as the vectorial components, and D as the tensor part. For example, in the case of cosmology, the people thinking in the tensorial part to study the gravitational waves effect. And the modes related with the vectorial and the scalar components can be also studied. And in our case, the interest part is the scalar component, because it's the responsible to generate the inflation period. So let me show you. The full metric is right. Let me remove the Windows part. Okay. In this expression, we can codify the full perturbations with scalar, tensorial, and vectorial modes. If we want to study a situation in which you have tensorial modes and scalar and vectorial modes, this is the generic form. And in this expression, I performed a change of variables between the physical time and the conformal time. As I said yesterday, the only reason to write the metric for this moment in terms of the conformal time is because we want to simplify the the calculations here. And in this case, we focus on the scalar perturbations by choosing a diffeomorphism in such a way that the Newtonian norm, I mean, when we consider this F here, F up here, and this A equal to 0. This F and this V equal to 0, and this A equal to this quantity, and this A is a gauge selection, is equal to this quantity. So we obtain a particular form for the perturbed metric. So I try to say, we're going to work with the scalar part. So in that case, we can take only the part for that components of the metric. So we're going to consider this F and B equal to 0, and the A part that is vinculated with the time part here, and the A part which is related with the space part are equal to these quantities. These quantities we can write the quantities in the full metric. And this in many scenarios, go ahead. Okay. In many scenarios in inflationary models, the people work with this expression because they thought, okay, I want to consider the equations only with the scalar modes. So they perform this kind of elections. Again, the 0-0 perturbation is related with the time, and this perturbation is related with the cross terms, and with the special part is this is this kind of perturbations, and we can rewrite each of them in terms of components. For example, the time part is right with this quantity that at the end get a specific value, and the part that codifies the space sector is right in this form in terms of this function in this component f and this g. And here we consider that the change of this g is equal to 0. So we obtain a generic form for the spatial perturbation. And this is the form right in 7th. But also this form is right in terms of a new component, A, B, C, and Ci and Ci. And in each of them, you can see that the perturbation part of the disturbance part dependent on the position and on the time. So in this case, for example, we have using that this derivative is equal to 0. We don't have a change in this quantity, and also for the tensorial modes. A, F, A, and B are known as scalar parts of the scalar perturbations. Why? Because this A is related with the perturbations along the time, or to get an idea. And this V, for example, is part. V is part of the terms that affect the space sector, and also for the F case and for the case of V. And now we can read the full metric here in 8 in terms of A that have a relation with the time, with F, and with A and B. So those terms are the scalar part, and then we're going to choose an election with this quantity that appears here and with the quantity that appears here in the spatial part. And the other terms that involves the cross terms and involves the other perturbations in the space are equal to 0, the F part and the B part component. So we only still working with the with the part that have terms with A and with A and with E. And we have this expression, and we write this A and E in terms of psi and phi. Again, this phi represents is not related with the field. And also we can consider the first order perturbed equations from the Einstein equations, and we're going to obtain this equality. In this equality, if we consider the boundary conditions for this equation, implies that the both variables are equal. And when we make that kind of election and put the boundaries conditions, in many references, you can see that this variable has the name of Newtonian potential. And this Newtonian, in that case, we can write the metric again in terms of this psi, and this psi appears here and appears here. So now we have obtained an expression that in both terms, in the time part and in the special part, have the Newtonian potential. So that is the justification to write the metric in this form. As you can see, in this part and in this part, we have the same quantity, the Newtonian potential, and also we came back to the previous lecture it's the same. The previous lecture, 2, 3. And we mentioned yesterday that the connection between the observations and the theory is with could be with this equation, and this equation relates the temperature with the Newtonian potential, and this quantity now we know that appears from came from the perturbation theory when we made a choice of the gauge, and we decide ignoring vectorial and tensorial modes. We work with the Newtonian gauge, and it gives also the Newtonian potential. And the people try to study the Newtonian potential and get the relation with the temperature using the Sachs-Wolf effect. The people measured the redshift, as I mentioned yesterday, from the last scattering surface, try to get the temperatures of different points, and then compare the difference with this quantity. So please let me know if you have questions. Yesterday, someone asked me about this quantity, this relation at the end. So if you have questions, go ahead. Okay. I'm going to share again the presentation. Now, we have a justification to equal these quantities, because we ignore the vectorial, the tensorial perturbations, and we did a choice of the gauge. We choose the Newtonian gauge, and we have the expression in terms of this Newtonian potential. So, to account for the emergence structure, we consider in the standard treatment, I write the standard word because tomorrow I'm going to present a different analysis for the structure, and I want to distinguish between the standard analysis and the analysis with I work on my researcher. And let me explain first of all what is the state of the standard treatment in terms of the perturbation theory of the metric and the field. And at the end of this lesson, we're going to analyze the questions on this model. What are the problems that inflation paradigm still have, and how to get the advantage of the inflation, but work with inflation in a different way. So this will be the final part of this lecture, but we're going to start with the perturbations of the metric and with the perturbations of the field. As I mentioned, the field is separated in modes. This is the zero mode of the inflation field, and the other modes are dependent on position and on time. And we can make an election of the gauge, as I showed in the previous slides, and we obtain this expression for the geometric part. And for the field, we can work with this with this full field, but we try to relate both quantities. I mean, the quantity to describe the field and the quantity to describe the perturbations of the metric, because we know in GR we work at the same level, the space-time part and the matter part are related using the Einstein equation. So we try to write both quantities in terms of the same variables. And you can notice that using these variables, you can write a new term that involves the perturbations of the field and the Newtonian potential. I didn't write delta here because this quantity is already defined the perturbation part. So it's not necessary write delta G because the perturbation component is here and here. So I'm looking for a variable that work together or at the same level, the matter and the geometry. And those variables are introducing in many papers of Vardin and other authors. But in Weinberg, you can find the analysis. I try to summarize, and maybe the notation here is a little bit different, but the essential part is the same. So now you have these new variables in terms of this age. Remember that this age talk about expansion. And one proceeds to quantize this variable because the people thought, okay, now we have an scalar field, and we know how to treat with fields because they know very well the quantum field theory and also the GR part. So the idea was the following: they try put together at the same level the matter and the geometry, and also they try to connect the perturbations of the field with the perturbations of the space-time. Then they try to relate using these variables and thought, okay, we know this is a quantum field. We can give a treatment in terms of quantum theory. So that was the reason, because they try to quantize, but you can see from these equations that they try to describe the both quantities, the perturbations of the field, and the perturbations of the metric in one variable. So when the people quantize this variable, is also because the people try to quantize both of the elements of the theory, the matter part and the geometry part. So we can put a note or do a note. And one question that I expected at this point is, why is the reason? Because you try to quantize the Bott perturbations. Why is the reason? Because the people, I know the quantum field appears here, but now they put the perturbations in the metric and they try to quantize Bott. The perturbation on the matter and the perturbation on the background. As I mentioned yesterday, we are interested in the study a period after the Planck era, because despite of many efforts, we don't have a successful theory for quantum gravity. So we don't know how to deal with that kind of features. And we can study the following period, that is the inflation period in which we are deep now, but we don't have or there are many possibilities to study this period, because it's a period, okay, after the Planck era, but how to talk about the quantization part. I started to talking about this topic because I'm going to deeper at the end. And again, using this variable that involves the Bott terms, the people quantize and using the annihilations and creations operators, constructing the Fock-Hilbert space. And the form that the variable with has is the following. So in this expression, they consider both the creation and annihilation operator, the variable, in terms of the perturbation of the field and the perturbations of the metric, and proceed with the quantization method. So in this expression, you can see that we have, as in, it's similar that when you quantize other quantities, for example, in electrodynamics, it's a similar method, but in this case, it's good to see that we have two parts, and we have this quantity that codifies the modes of positive and mode of negative frequencies. What will be the way to choose the modes? The people, as in many scenarios of GR or in quantum field theory, they thought, okay, we know how works on Minkowski spacetime. So I thought that in the remotely past, the universe could have the form of Minkowski spacetime. So I try to study the modes with a frequency according to the Minkowski spacetime. And they tried take this limit to study the remote past and then try to study the modes that behaves as in Minkowski spacetime. I meant the modes with positive frequency from this expression. And could be a full class, take the conditions for how to choose a particular vacuum state is an area of study, still being studying, because it's not trivial how to choose a particular vacuum state, but the people try to choose a specific vacuum state with the definition of generic vacuum, as you know. When you use the annihilation operator, you can define a vacuum state. In this case, when the people look in the remote past using this conformal time goes to minus infinity and try to see what are the modes with positive frequency and put the conditions on the vacuum here, they get this expression to define this is the generic for every vacuum, but they use a particular state well known as the Bunch-Davies state, and is so called the adiabatic vacuum state. In the case of the slow rolling model, as yesterday we can study yesterday the slow roll mechanism to describe the expansion. So the name of the adiabatic vacuum is related with the densities and the and the pressures part, because putting analogous between the statistical part and the matter that we consider in cosmology, they try to get the conservation equations and they put names similar. For example, they consider the adiabatic perturbations in terms of the pressures, as I'll show you. And they also could consider a different kind of perturbations related not with the adiabatic part, not with the densities. They could consider in terms of quantities related with the energy conditions, for example, and they could use the entropy perturbations, and then they could have a different kind of vacuum. But in this case, we're going to focus on the Bunch-Davies. In the Bunch-Davies state, the Bunch-Davies vacuum is a particular state characterized in the remote past, and the modes that we're going to choose are the behaves as in Minkowski spacetimes, I mean with positive frequencies. And now, as yesterday, we studied, let me show you first this slide. And yesterday we talked about the Harrison-Seldovich spectrum. In that case, the people write in terms of Fourier transformations, and what Harrison-Seldovich tried to study what happens with the spectral characterization when put, for instance, the density fluctuations. Also, yesterday, we studied the differences between the kinds of fluctuations. We studied the space-time fluctuations and the statistical fluctuations. And we mentioned that in the case of the density fluctuations, we have the model to describe how change one quantity from one point to the other. And in this case is the density. Here, again, the people using as a model the Harrison-Seldovich spectrum, they study what happened with the fluctuations on the density. In this case, they consider the relative density fluctuations during the inflationary regime, because yesterday the characterizations in terms of the spectral quantities was thought in an epoch in which the people thought that the universe was feeling for radiation dominated by radiation matter. But in this case, we want to consider that the matter is radiation. We want to study what happened with the structure according to inflation theory. And inflation theory, as we studied yesterday, inflation theory is characterized by an effectively cosmological constant. And that constant is contribute with the matter. So instead of have radiation, we're going to have a cosmological constant. When we try to write the Einstein equations in the part of the energy momentum tensors, we write a cosmological constant. We know that it's an effective cosmological constant because we are interested in that the inflation period ends, but could be right in terms of the as a constant in the Einstein equations. So we write the density fluctuations, but when I mentioned that the fluctuations are taken in the inflationary regime, I try to say the matter is cosmological constant. So this is a first, not exactly the first, but it's one difference between the Harrison-Seldovich characterization and this framework, because we have we know that the matter sector is different. And also, in this case, the people thought that this density is a special average of the universe density. So be carefully here, because the people thought first the space-time fluctuations, because they try to get the density in different points here in this first part, but also they consider the spatial average of the universe density. So in this point, they consider the statistical fluctuations, and in this quantity are involved both the space-time density, I mean the space-time fluctuation and the statistical fluctuation, but only in this quantity. And this quantity represents a fluctuation in the CMB. So again, now we know that the people read the temperature of different points, a different pair of points, and they try to study or try to connect with the Newtonian potential, and also they can study how the density changes from one point to other. But again, it's important when we read the word fluctuations, be carefully or read with careful, because it's not easy, or could be easy, thinking statistical fluctuations only, but lose that we have also the space-time fluctuations. And here is not really, it's not a problem, but I'm going to introduce the problematic part, because here we try to describe, or the people try to describe at the same level, the matter sector and the fluctuation, or the perturbation of the space-time. Then they try to quantize, they obtain a particular state that is the Bunch-Davies state, and then they mention, I want to consider the fluctuations, the density fluctuations, but here the density fluctuations represent this quantity that change from one point to the other, and also they take an average of the universe densities. And then they try to quantize, or they try to obtain the 2-point functions for this pressure. Sorry, I forgot the row here, but the power spectrum they try to looking for a primordial inhomogeneities of the spectrum, because they try to put, and also it's similar to the work of Harrison and Seldovich, because they also consider the perturbations of the background. They have the Newtonian potential, but they haven't the part of the inflaton field. So here, the difference between the Harrison-Seldovich spectrum and this spectrum is that the matter sector is characterized by the inflaton field and the perturbations of the inflaton field. And furthermore, this variable have both the perturbations on the field and the perturbations on the metric. So when they try to relate that quantity with this quantity, they perform the 2-point functions, but here they try to study the differences on the, for example, in this case, the density between the one point to other point. In that sense, this quantity is named as the 2-point functions, but also they try to write the quantity in terms of the variables that I show here, because they have a way to relate this quantity with the pre-Ashers, and then they get this expression. And this expression is known as the 2-point functions, and the people study or try to connect the 2-point function to study different points in the whole sphere, and try to get the power spectrum, try to extract this quantity. This is the interest quantity, but let me tell you the relations with the with the Harrison-Seldovich spectrum, because here again, sorry, I forgot to put the variable rho, but you have this quantity depend on x and depend on different points here. But this k has a different meaning than in the Harrison-Seldovich spectrum. In the Harrison-Seldovich, we thought I'm working in the Fourier spacetime, and we try to characterize in terms of k's that represent the Fourier space, but is also related with the spectral characterization. In here, we try to give a characterizations in terms of modes of positive and negative frequencies. We made a choose of the modes, and we choose the modes that have a behavior similar as in Minkowski spacetime. I mean the positive frequency modes. And with that election, we can see that here, this case represents a different thing. In this case, we have that this case codify the modes of the inflation field. So this part, let me back. I have. This part could be represented as a sum. The sum of modes from 1 to infinity. I separate this mode because this mode is independent of the position, but the other modes could write in terms of the sum. For example, the 1 mode plus the 2 modes and so on. And when we talk about this K, we try to represent the level of the modes. So we have a similar expression as in the power spectrum of Harrison-Seldovich, but in this case, the quantities have a different meaning. So in this case, the quantities are vinculated with the modes the number of modes. And the quantity here represents the power spectrum of density fluctuations, as in the case of Harrison and Seldovich. So we should be careful because the expression is similar. The expression has many common things, but the meaning is different. So again, in this spectrum, we try to read the statistical part using the correlations. But where is the statistical part? The statistical part is only here because the people consider the spatial average of the universe density. But when the people try to compute this quantity, in this case, this quantity is right using this form. This is the Bunch-Davies vacuum that we constructed here, because as I mentioned, you can read more about the Bunch-Davies vacuum from the Weinberg's book, or also using the Leonard Parker's book, and you can read how to get this particular vacuum. What is a vacuum? Which has the symmetries of the spacetime, the homogeneity and the isotropy part. So we have, because we choose the modes that represents a positive frequency, and we have also the Bunch-Davies vacuum with the same symmetries as the spacetime that we constructed. But now, if we are interested in this quantity, in terms of the quantum part, we need to map this quantity to this quantity known as a 2-point function, as I mentioned before. And again, this quantity is related with the matter part and with the geometry part. So, as in many things in quantum field theory and in quantum mechanics, we need a state to compute this quantity, and this state is the Bunch-Davies vacuum. So for this expression, we can read many things. One of them is that we try to quantize one part of the matter and one part of the spacetime. In the second is that we try to compute this 2-point function in terms of writing in terms of the Bunch-Davies vacuum. This Bunch-Davies vacuum has the symmetries of the spacetime that we use in the background. Is a state which is invariant under rotations and under translation. So the people try to write this spectrum, extracted the spectrum using the 2-point function. This is the same part that appears here. But again, in this part, this case represents the modes, and this quantity represents the 2-point function. In the 2-point function, you can compare again what kind of fluctuations you have here, because when the people try to put by hand a statistical mechanism, they try to write in this form the power spectrum, but it's not they haven't quantized here, so they only consider an average between the quantities along the sphere. But in this case, if they try to quantize and try to write the spectrum in terms of the 2-point function, instead of have an average, they're going to have this quantity. And the people, and the first not clear part appear here because the people try to read this quantity in terms of an average, or not just in terms of an average. The people try to read this part using the word fluctuations, because in the literature many times the 2-point function is or has the name of quantum fluctuations, but quantum fluctuations, yesterday we studied the differences between between the space-time fluctuations and the statistical fluctuations. And I mentioned, so far we only have studied the two kind of fluctuations, but tomorrow it will appear the quantum fluctuations. In the literature, the people know this quantity as quantum fluctuations, and they try to read from this expression what are the common characteristics between this quantity and this quantity. Because they obtain, when they try to perform, when they performed this expression, they obtain this result. Using again the density fluctuations, but this expression that worked very well since the time of Harrison and Seldovich to represent the structure of the universe is obtained for the 2-point functions, and considering the density fluctuation. So when the people reproduce the same form for the power spectrum, the people was really happy with the inflation period, because they argues that one could argue that quantum fluctuations are generated by the inflaton. So this could be the end of the whole early universe course, but there are many questions from this expression, because we could ask, okay, but in that case, you consider an ensemble, as yesterday we studied. Yesterday we mentioned that in this case, we're going to consider an ensemble of possible universes. And the ensemble represents a statistical distribution. But the assumption was taken here. And then Harrison and Seldovich focused on a particular quantity, the density, and compute the power spectrum and obtain these forms that, in the particular case of n equal to 0, is scaling variance. We have this form, and this form represents the structure of the behavior of the structure. And what is the integral part? But they consider the two things. One of them is the ensemble of different possible universe, and also they consider the fluctuations of one particular quantity. And in this case, this case represents that we are working in the Fourier space-time. We are trying to formulate quantum fluctuations or statistical. Yes, this is the part that I want to address. because yesterday we studied the statistical treatment in terms of the spectral characterization. And today, we want to study, or we try to study, is the same. We try to study the quantum part in the standard framework. And in the quantum part, the people try to try to compute this quantity and put at the same level as the statistical part. But it's a mistake that the people take here, because again, it's important to emphasize in the distinction between quantum fluctuations and statistical fluctuations. Let me show you again the differences between them. In the quantum fluctuations yesterday, we mentioned that this type of fluctuations only talk about the indeterminacy of the wave function, for instance. And we study a particular case of the harmonic oscillator, and the fact that the ground state of the harmonic oscillator has a weight represents the fluctuations, I mean the uncertainties. So we understand uncertainties as quantum fluctuations, and it's completely different the meaning for the statistical fluctuations, because those are associated with a big collection of objects or assembled, and in that case, each of the components of the ensemble have a particular weight, and in the characterization that the Harrison-Seldovich used, they taken into account the statistical fluctuations and the space-time fluctuations. But today, I presented the quantum version using inflation era to describe the structure. And the people try to use the power spectrum from the 2-point function. But the 2-point function is a quantity, is a quantum quantity, and is computed with a particular state, the Bunch-Davis state. And I try to compare with the statistical correlations and try to compare that the 2-point functions represent quantum fluctuations, and the characterizations in terms of Harrison-Seldovich and or the power spectrum before inflation that the people used before, used before, is right in terms of the ensembles. But here, this quantity is writing in terms of the 2-point functions part. So this is related with quantum fluctuations, but not with the statistical fluctuation. And why is important to talk about the kind of fluctuations? Why not take as synonymous? Because, for example, in statistical fluctuations, you could have an stochastic component, or you could have an extra component to break the symmetry of this state. This state, as I mentioned before, has a particular symmetry. The symmetry is the disinvariance on the rotation and on the translation. But the invariance of this state need to be broken to give account for the structure. And if the people thought that the fluctuations are statistical, okay, in that case, they could have an ingredient, a stochastic ingredient to break the symmetry. But that is that thing that I mentioned is not true, because this quantity is associated with quantum fluctuations, and quantum fluctuations are vinculated with uncertainties, not with an statistical component. So you can write the spectrum here and obtain the same form. But what is the explanation for the breaking of symmetry? You don't have a good explanation for the breaking of symmetry. Let me read one question that is in the chat. So in the statistical case, we take an ensemble of multiverse. Okay. And in the quantum case, we are talking only of a single universe? Okay, yes. That word in the multiverse sounds I don't like the word, but you're right in the sense that we consider an ensemble of different universe, but we only think on mind or keep on mind the idea that in order to perform the integrals and in order to take an average, we need to think in an hypothetical situation in which we have different universes and we extract the measurements from different universes. But the fact is that we only have access to one universe, and we can read the same measurements on the same universe, and then try to write all the measurements in terms of measurements from different universes. This is the people say that they take ergodic arguments to represent the ensemble. But as you mentioned, here the people haven't considered the ensemble. They only consider the 2-point functions. This quantity related with the matter part, because it's right in terms of the fluctuations of the inflaton, and the same quantity is related with the Newtonian potential, so has the two elements. But they only take the 2-point functions. They never take an average, because as you mentioned, we only have one universe. And if we want to compute the 2-point functions, we need this quantity. But the argument is different, but the people said, okay, but the 2-point functions give us the quantum fluctuations. So if we have the quantum fluctuations here, and we have the statistical fluctuations from the other spectrum, that's all. It's that the people say, it's not my claim. So they try to use this quantity, in this case, as you mentioned in the question, we consider an ensemble of possible universes in this case. So this line represents an average. And we have the element to describe in terms of a spectral characterizations, the structure. They give a particular form and they obtain this form. But now it's a different treatment. I mentioned one difference between the first approach is that in that case, they consider that the matter component is radiation. Here, we consider that the matter component is cosmological constant. So we have cosmological constant, and then they try to relate the perturbations of the matter, the perturbations in the space-time, and quantize them. They quantize, and using the 2-point functions, they write and try to represent the power spectrum. And they could extract the power spectrum from this equation. And from this equation, if they compute what is the form for the power spectrum, they obtain the similar result. But it's important to study the details of the meaning of the names that we use. Because, okay, again, this is named quantum fluctuations, but it's not an statistical characterization. It's, we don't have a new element to break the symmetry. So what is the physical idea that we want to describe? We want to describe how the first cosmic structure appears. But that kind of structure appears from an homogeneous and isotropic universe. So, as one asked in the first lecture, how we can take that kind of symmetry to represent the structure. We need perturbations on the matter and perturbations in the background to represent the structure. But also we expect that at this point, when we consider the 2-point functions, these 2-point functions is right in terms of a particular state. And this particular state, known as the Bunch-Davis state, has the two symmetries because it was constructed in terms of the symmetries of the background. It's a state invariant under rotations and under translations. So if we want to generate or give account for the structure, I need to break the symmetry of this state. And the people usually argue that the quantum fluctuations broke the symmetry of this state. But how the people, or how they show you? Why is the reason? Because they thought that the 2-point functions broke the symmetry. The reason is because they have a misconception of the definitions of fluctuations. It's really important distinguishing cosmology between quantum fluctuations and statistical fluctuations, because there are many problems in cosmology regarding this confusion. If the people take this fluctuation as in a proper way, and we say, okay, this quantity represents the uncertainty, you don't have an ingredient to break the symmetry. And it's impossible give a logical or a clear theory for the structure. You can obtain the same result as I show you here, but what is the meaning of, what is the conceptual part of this framework? You don't have a good conceptual part. You have the same equation, you reproduce the same form, you also, this expression allows us to connect the observation with the theory, and you can still working with this expression and all is good. But if you try to give a theory, a clear theory, you need to address the problem in terms of the differences between the statistical fluctuations and quantum fluctuations. Then, when you recognize that quantum fluctuations are different to the statistical fluctuations, you recognize it also that you don't have an element to break the symmetry here. In quantum mechanics, for example, when you have the expectation value of one quantity, or you have an operator, as yesterday I described the ground state, of the harmonic oscillator, you have the uncertainty because you don't have the exact value of the quantity. What the theories tell us about that feature, the theory said, when you perform a measurement on the system, you get a particular value of that state, and you get an eigenstate. And this eigenstate represents the value that that operator takes to the state collapses, and you have a particular eigenstate. And you have a particular value of that quantity. But what is the ingredient that you use to break the symmetry of that Gaussian? In the case of the ground state of harmonic oscillator, we performed, or the people performed, a measurement. Okay, and we know that at the level of quantum theory, measurements are written in terms of observations or a measurement device. So in this case, we can ask, or you can ask, okay, but if you, to explain the structure, it's necessary break the symmetry of this state. But we note from quantum mechanics that to break the symmetry, we introduce an observer or a measurement device. Okay, so we have an idea to break the symmetry here, and is perform a measurement, or is an observation, a measurement, but the question is, okay, you are working, or we try to describe the early era of the universe. So how the structure is generated without, or what is the observer at that point to generate the structure? What could be a good measurement device in the early universe? It's a really hard question, because the people could argue, okay, you could perform a measurement and then you break the symmetry of the state. But okay, who is the measurement? Who measure at that point? Who measure at that time? And one argument that is funny, because it's not a really good argument since my point of view, the people many times claim that we can see to the CMB, and then in that sense, we perform an observation and then perform a collapse on this state, and we get the structure. But this paradoxical is funny in that sense for me, because they try to describe the structure that forms the planet, the galaxies that even form us, with an observation, because it's a cycle. It's a model that is not a really good explanation since my point of view, because we are formed for the same structure that when we observe collapse and form our structure, it's not really clear. But there is a new. Cannot we understand this symmetry breaking as kind of phase transition between the two states, which is excited by by quantum fluctuations? Again, you can think in a phase transition, but the phase transitions, how the phase transition could break the symmetry of a quantum state. And in that case, for example, you mentioned at the end, which is excited by quantum fluctuations. But quantum fluctuations are only describe the uncertainty. So you can have a phase transition, but the phase transition is a transition that could explain in terms of the spectral characterization level. But in this case, you try to describe the expansion of the universe in terms of a quantum field. So we know how to deal with quantum fields. The people perform the quantization, then obtain the 2-point functions, and from this expression extract the power spectrum and obtain the same result as Harrison and Selvage. But in this case is the quantum framework. But in order to break the symmetry, you need an extra component in the quantum framework. You could get a described in terms of the statistical part, and you can give an statistical treatment for the densities, and study the phase transition and study in terms of a fluid. But if you try to describe the early universe in terms of a scalar field responsible to the expansion, you need to give a quantum treatment. And when the people try to address the problem in a quantum framework, they attempt this problem now because they don't have an ingredient to break the symmetry. And if they try to incorporate the ingredient in terms of the quantum theory that we study in the former level, we realize that the collapse implies the necessity of an observer or a measurement device. And in this case, it's a philosophical question: who measures in the early universe? And sounds like a philosophical question, but it's a real question when we try to describe the model. And tomorrow, I want to introduce a problem that is beyond the philosophical arguments, because at this level, one question could be, okay, but you have the equation, and if you have a good equation to connect with the observations, that's all. You have a way to do predictions, and the quantum theory, who cares about? But if you try to study several problems that appears in the theory, you can realize that you need to study, or you need a good explanation, first of all, for the structure. You need write the breaking of symmetry without or removing the notion of an observer. So the question now, we have many questions at this point. One of them is how describe the breaking of symmetry in the 2-point functions. One possible answer is using a collapse, but then appears the question, who measure in the early universe, or how write the measurement without observers or without tools to measure. And other question could be, not exactly in this topic, is you mentioned that we study an era after the Planck scale. So we don't have a successful gravity theory. So what are the arguments to quantize one part of the space-time? Because as I mentioned yesterday in the beginning of this talk, I mentioned that this quantity is right in terms of fluctuations and in terms also in the perturbations of the metric. So a different question is, could be, what is the reason to quantize one part of the space-time here? And the second question is, okay, you try to quantize, you try to write the power spectrum, and then you don't have an ingredient to break the symmetry. Tomorrow, I'm going to present a different way to address the inflationary paradigm in terms of semi-classical gravity. I will present a theory in which we only quantize the matter part without the space-time part. the first difference. And then I try to write this quantity with a new ingredient. But in order to incorporate a new ingredient to break the symmetry, we have to study the measurement problem in quantum mechanics. And when we study the measurement problem in quantum mechanics, we have the tools to develop a theory in terms of a quantum theory that involves in the equation not only the quantum fluctuations, in a quantum treatment that is right also in terms of statistical fluctuations. Because at this point, when we try to compute the 2-point functions, we only have this kind of fluctuations. We need the statistical or stochastical part, but we haven't that kind of fluctuations. If we try to incorporate the statistical fluctuations at the level of quantum mechanics, we need the incorporation of an observer or a measurement device. And it's not clear who measured at that epoch or who observed it. So we need to write a new theory in terms of statistical fluctuations, but removing the notion of a measurement device. So please let me know if you have questions. There are topics here that is not easy to explain, so I can reformulate the arguments, or I could try to explain in a best way. So if you have questions, please go ahead.
Well, I don't see anything in the chat just yet.
I
People are free.
have answered the questions that appear in the chat. Did you see the questions?
Oh yeah, but you addressed them all,
Yeah,
at
yeah,
least the
yes.
ones that appear to me. Yeah. So if people want to unmute themselves, they're free to. If they want to type something like while you type, let me ask one question. So when you constructed, well, you didn't construct, but when you mentioned that in the standard approach, people use the Bunch-Davies vacuum to compute those 2-point functions. You mentioned that it's defined when the conformal time goes to negative infinity.
Right.
So does that mean that we are assuming there is an inflation period necessarily? So this is necessarily assuming that there is an inflationary period, so we can approximate the de Sitter space-time and define the vacuum state there. Is that right?
Yes, it's right. And we consider, and let me tell you something and tell me if I understood in a proper way your question. But the point is, you only consider this conformal time goes to minus infinity, and it seems that the inflation period is not considered here because, or I assume that inflation period starts from minus infinity. Yes, it's not a really good assumption here, but it's we thought that minus infinity describe the inflation period, but it's not really clear because also we know that before inflation, we had the Planck era. So we thought the Planck era before minus infinity sounds not clear, I know, but
right.
the way the people define this Bunch-Davies vacuum is in this way, and actually there are many arguments that say, okay, you can still work with Bunch-Davies vacuum, but it's not necessary described in terms of the inflation period. So they try to describe early universe of the expansion using a different framework, not exactly inflation, and still work with the Bunch-Davies vacuum. So in that sense, it's a bad point in our theory. I recognize that point. There are many works about how to choose a a good vacuum, and there are many other other options to work with vacuum, not exactly the Bunch-Davies vacuum, and they try to explain all kind of things in terms of different vacuums. But it's a good question, and it's good to emphasize also the problems of this paradigm.
Very good, thank you. Yeah, there is a question and a clarification of why we use a quantum collapse. The person says,
Okay.
I didn't get very well the observer at the beginning of the universe question. Oh yeah, so I'll hand it to you.
Okay, let me read the question. Also, because I didn't hear you very well. I'm not sure if it's my connection, but let me read again the question. Thank you. I think I would like a clarification in why we use a quantum collapse. I didn't get very well the observer at the beginning of the universe question. Okay. The people try to reproduce the power spectrum in terms of the two-point functions. So they try to write the two-point functions, but these two-point functions is right in terms of the Bunch-Davies vacuum state. The Bunch-Davies vacuum state is a state invariant under translation and rotations. So you have a symmetry here in this expression. The symmetry originated, or the symmetry that the Bunch-Davies vacuum have. And then the people argue that using this form, this two-point function, they extract the power spectrum. They could explain the generation of the primordial seeds of cosmic structure. You know that the point from we started is a point in which the universe is homogeneous and isotropic. But if you now try to incorporate the matter in the structure of matter, the primordial seeds of cosmic structure, you need to break that kind of symmetries in a proper way. So that was the reason, because we incorporate the perturbation theory at the level of the space-time part and also in the matter part. And then you recognize that this is a quantum field, so try to give a quantum description of the field, and then write this quantity in terms of the Bunch-Davies vacuum. And you have the symmetries intrinsic here. But in order to generate the structure, you need a mechanism to break the symmetry of this state. So you don't have that ingredient. You can perform this integral or extract this quantity that is known as power spectrum, and you get the same quantity as in the Harrison and Seldovich spectrum. But that quantity, this quantity, represents the structure. But if you try to analyze what happened here, you realize that you can get the same expression, but you don't have an ingredient to break the symmetry here. So if you don't have an ingredient to break that symmetry, you don't have an explanation to generate the structure. So this result has not a good justification. You could use the result and connect with the observations, but if you try to have a good explanation for this quantity, you need to incorporate a mechanism to break the symmetry. Many times the people say that this quantity is related with quantum fluctuations, and they take as synonymous quantum fluctuations and statistical fluctuations. But as we studied before, we have been studying along this course that quantum fluctuations are different to the statistical fluctuations. And the quantum fluctuations only tell us about the uncertainty in a wave function, the uncertainty in some quantities. But here, if you try to incorporate an ingredient to break the symmetry, you could perform the people mentioned. You could get a collapse, and then when this quantity have a collapse, you break the symmetry of this state. But in quantum theory, collapse is right in terms of an observer or a tool device to perform the measurement. So you don't have an ingredient at this point, you don't have an ingredient to represent an statistical fluctuation and don't incorporate an observer or a measurement device. I don't know if now is more or less clear, but we need describe these 2-point functions in terms of statistical fluctuations, but removing the notion of an observer to avoid the questions of who measured in the early universe, because are questions that have no. Okay, and so collapse is that mechanism? Yes, collapse, if we try to incorporate collapse, the problem that collapse have in the standard quantum theory is that collapse is written in terms of on observers or tool devices. So tomorrow I present to you a theory, a different quantum theory, removing the notions of observers and removing and work with a theory that work with quantum fluctuations and also work with statistical fluctuations, but without the notion of observers or measurement devices or other weird things.
Are there any other questions? It was a dense lecture, so let me ask you again. And are there any other questions? People trying to encourage people to not be shy and ask questions.
You can ask in the chat or now. In the first 2 lectures, someone asking a direct chat. So if you feel more comfortably in the direct chat, you can also use that via. But maybe a good clarification could be that the perturbation theory part works for the both for the spectral characterization and for the quantum characterization, because I write in this slide and maybe it was bad idea right here. Could be better if I write here this part before the spectral characterization, because the people who work with the spectral characterization also use this part. So this way to write the metric works for both, for the spectral characterization and for the quantum framework. So it's good. The good point is that I haven't sent you the last slide, so I can change the order of this perturbation part and put in a way that they try to see that this englobes the whole, the both characterizations. Okay, no, the question is about the link, not. So, do you have any questions?
Yeah, I don't see any other questions, so perhaps we'll end up here and we'll see everyone again tomorrow. See you then.
Yes, thank you.